Hi, this is the talk on Go-Landlock. I'm Günter Noack. I have been working on Go-Landlock for a while now, and also occasionally on the underlying kernel feature. So I already said it. Landlock is a library that depends on a kernel feature called Landlock, and it's a sandboxing feature. So what you can use this for is if you have an application that is running as a regular user, for example, because the binary gets shipped just in a normal Linux distribution package, then you can use Landlock, and you can use also the Go library for it or the Rust library for it in order to make that application drop its privileges and to run the application in a more constrained environment where if an attacker takes it over, it can't do that much harm. So let's have a look at what that means. So this is the high-level overview of an attack. At the very high level, and this is a very high-level depiction here, you have an attack process, and the attacker is going to attempt to gain control over it. Gaining control can take many forms, right? So in the extreme case, it's a buffer overflow exploit, and that means that the attacker can actually gain complete control over the process. It can override assembly instructions and make that process execute instructions that are provided by the attacker. That's a case where the attacker essentially gains the same rights as the process already had. There are, of course, other cases how an attacker can gain access. There is, for HTTP servers, for example, there are directory traversal attacks as a classic, but also other ways. And the problem with these is that if the attacker has gained more access than the process was meant to provide, then potentially the attacker can talk that process into giving him access to other things that the process has access to. And now the problem with this is that Unix processes tend to have access to a whole bunch of things, such as this: your SSH keys, your cookies, your bank documents, love letters, your Git repositories. So this is quite a collection of interesting material for an attacker, and it's really unnecessary in many cases, right? So an attack process, for example, it might be a web server that serves one directory and has a bug, and then the attacker gains access over it, and suddenly the attacker has access over all kinds of things. But for the normal operation, this web server didn't need all that access. It was perfectly fine. It would have been perfectly fine if that process only had had access to that directory that it was serving. And there are other examples like that. So this is called the ambient access thing, right? So with this ambient access where process has access to all these things in its surroundings, processes have more access than they need. And so the obvious solution is we should be limiting this. And there have been, let's talk first what kinds of let's have a look first at what we do in practice already, right? So in a normal talk, I am asking questions now, and these questions are you running your software in a container? Are you running software runs outside of a container? Have you tried to sandbox that software yet? Why haven't you? So it turns out the reason for why people don't normally sandbox their software is it's actually really hard to do. There's a whole bunch of technologies that have to do with sandboxing, and they're kind of difficult to use. They are not deployed in all kinds of environments where you would like to deploy them, or where you would like to run your software. Sometimes you can't rely on the system where your software runs to have certain software installed. So this is particularly true for containerization. If you just provide a binary, you can't assume that everyone who wants to run that binary has some containerization software like Docker installed. Or you can't assume that someone who wants to run a binary has AppArmor or has SE Linux installed. So these are problems, and also then other things are namespaces, but I'll get to that. So one observation, is the cost is too high for sandboxing, and we would like to turn that around. And this is one of the main ideas, to turn this around so that the cost becomes much lower and we have roughly the same benefit. Now, the other big idea in Landlock is that we do trust software authors generally to do the right thing. So the idea is that sandboxing becomes part of the application that is being sandboxed. And it has also a technical reason. So the idea is basically that you have an initialization phase of your program where you open the necessary files and sockets. And then comes the big yellow phase where you drop permissions. And from there on, your process doesn't have the permissions anymore that it had at the initialization phase. And only after you have dropped permissions, you start processing untrusted input. Now, the twist with this is all of this happens within the same Unix process. And a lot of existing sandboxing technology is sandboxing processes from the outside. So there's a whole bunch of permissions that you can't drop that way, right? You want to run a web server, you need to somehow open the network socket for that. And you have to do it in an initialization phase. If you have your sandbox all the way around the entire process, you need to provide that permission. If you do it after the initialization phase to drop your permissions, this file descriptor will already be opened. And access rights in Unix, they are checked at open time and not at the time of using this file descriptor. So you can drop more permissions that way if you do it that way. So these ideas are not new. OpenBSD has pioneered some of this. The syscalls for that are called pledge and unveil. And pledge is similar to Linux's seccomp. It can restrict system calls. And unveil is somewhat similar to what we're going to see what Landlock provides in Linux. It restricts access to file paths and the hierarchies below directories. This is very lightweight to use. What OpenBSD has done is they've taken a lot of programs that are part of the OpenBSD distribution and attempted to make them pledgeable and unavailable. So they have found hundreds of programs that they managed to sandbox that way. And it's a very lightweight approach, and it's at the high level, this is the same approach that we take in Landlock as well. The other big sandboxing technology that exists is Capsicum. This is a FreeBSD technology and is part of the FreeBSD kernel. It's a capability model bolted onto Unix, and it removes all access to global namespaces when you enable it. Now, you can imagine that what that means in practice is if you call open to open a file, you won't be able to. You have to call open@, and provide the directory handler to a directory that you already have opened in order to access files below that directory. And you can imagine that this is quite a departure from normal POSIX semantics, that open never works. And so this is a sandbox technology that is a bit more difficult to use, because you can imagine that many applications will have open calls that you might have to hunt down and rewrite in order for this to work. And then there is, of course, unprivileged sandboxing on Linux. I'm saying unprivileged. This is funny because you would not believe that you have to be privileged in order to drop permissions. Dropping permissions should always be free, right? But unfortunately in Linux, a lot of containerization technology has to run as root. And this kind of technology I'm not even looking at, right? So the privileged category of sandboxing is, for example, AppArmor, SELinux. Those are things where you have to be the admin to enforce a policy on a program. Now, for the unprivileged part, there are two main things that you can do. One is seccomp BPF. It's a packet filter style filter that you can install for a program so that it filters the system calls that you do. And it's done in the same bytecode language that is also used for packet filters. And apart from that, BPF is of course also enables all kinds of other features, but Second BPF is the constrained version of BPF that is still closer to the Berkeley packet filter language. Now, Second BPF is hard to use. The reasons are not obvious, but I've tried it and it didn't work. So in order to filter the syscalls that your program does, you need to know what the syscalls are. And syscalls are numbers when it comes down to it. So there's a list of syscalls, it's a few hundred in Linux, that you have to go through and figure out which of them are supposed to work after enabling this filter and which of them are not supposed to work. And there are two main problems with seccomp. One problem is you can see the arguments to the syscalls as well, but you can't necessarily see behind the arguments. That means the first argument to the open syscall is a string pointer that points to the file name, but the file name is in user space memory and the system call filter in Second BPF doesn't get to see it. Now, there are hacks around that, but they're fairly complicated and not many applications manage to implement them. So, and it's also a major architectural change for your program if you want to use it. Now that's one problem with Second BPF. Another problem with Second BPF is the forward and backward compatibility becomes a tricky story. If you deploy your program today and you go through the entire list of system calls and you decide which of these system calls are supposed to work and which aren't, then you deploy it and the program works. But then a new kernel gets deployed on one of the machines where your program runs. And the new kernel has new syscalls because it's a new version. Now, there is this syscall that is now new. What do you do with it? Now you can decide in your program whether you want to permit it or whether you want to deny it. But you don't know what that system call is going to be. So you have to make up your mind. If you permit that system call, you might let the application do things that it wasn't supposed to do. So that's not an option. And if you deny that system call, well, C programs get linked with shared libraries. And glibc is happily going to start using newer system calls. It's well possible that the new system call that gets introduced in a future kernel is used by glibc, and then your program stops working if you deny it. So we're stuck between a rock and a hard place. We can't really tell into the future what these system calls are going to be that are going to be newly introduced. Now, the other option for doing unprivileged sandboxing is user namespaces and mount namespaces. Now, a mount namespace, both of these are part of the technology that containers are built on, basically. You can create a new mount namespace, and then that means that your program is going to have a different set of mounts that are enabled than the rest of the system has. And that's fine, but that doesn't let you restrict the visibility of files yet. So what you also have to do is you have to change the mounts there and maybe remove some mounts. But that doesn't work because you're not root. Now you also have to change into a new user namespace, and now that process thinks it is root. And if that process thinks it is root, then it can change the mounts within its namespace. And so it can change the mounts within the namespace, but you can already see that the process environment is going to look a little bit different suddenly. And also changing the user namespace and changing the mount namespace usually means that you have to invoke the process repeatedly and have only a child process do that. So also that initialization phase, then drop permissions, and then let the attacker send his input, that idea doesn't work there. And also it's fairly complicated. Now, let's see. Let's have a look at how to use Go-Landlock. Now, Go-Landlock is only one of many libraries that we have for Landlock. The other libraries are the Rust Landlock library, and there are C headers that you can use to just use the kernel interface yourself. And this is the architecture of it. So I discussed it before already. There is an initialization phase, and then there is the phase where we drop the writes. We use the Go-Landlock library for that. And then there comes the phase where we start processing untrusted input, and that is provided by this evil person here. Now, in the initialization phase, the user space Go program just uses normal system calls the Linux kernel, and the kernel does these on the behalf of the user space program. Now, then when we drop writes, we use the Landlock library, and the Landlock library is going to enable Landlock in the kernel for the calling thread. And when that is done, all the future system calls are going to get checked against the enabled Landlock policy. Now, if now the attacker starts to process, if now the program starts to process untrusted input and we get requests, all the system calls that happen on behalf of these requests are going to be checked against the Landlock policy, and the Landlock policy is going to tell which accesses are permitted and which aren't. So in order to use this, first thing to do is to make sure that the kernel actually supports it. This should already be the case because this is supported by default in a longer list of distributions now. But in case it is not, I'm going to explain it briefly. So first, it needs to be compiled into your kernel, obviously. And then secondly, it needs to be enabled at boot time, which means that you have to configure the command line that gets passed to the kernel in the bootloader and tell the kernel that Landlock is one of the security modules that you want to load. And if everything works, you can check whether it's already enabled with this command here. And that should print Landlock somewhere in the middle. Now, secondly, we're going to use Landlock. And what that means is you take this code snippet, adapt it a little bit, and paste it in between the initialization phase of your program and the phase of your program where you start processing the untrusted input. You might have to reshuffle your program a little bit so that the initialization phase and the phase where you process untrusted input are actually separate and happen one after another. So in this snippet here, you see what Landlock does. So you can use it to restrict what file system paths you can see and what you can use them for. And the way you do that is you just say out loud what you want to use going forward. And in this example here, we want to use the user and the bin directory for read-only operations, and we want to use the temp directory for reading and writing. Now, I am cheating a little bit because RODIRs and RWDIRs are just helper functions, but they're very convenient. They group together a lot of operations that you can do on the files in these directories and the subdirectories of these directories. So it's a shortcut, but there is still a way to do it at a more fine-grained level if you need to. Then at the beginning of this invocation, you can see I'm spelling out Landlock v3. The kernel Landlock feature has ABI versions, so we're going to use always the highest if we can, and then verify that the program works with this ABI version. If you have a program that uses Landlock that is already written and it uses an older version here and you have an opportunity to increase it, you should increase it. But you might have to double check whether this doesn't break anything. There is a small chance that if you increase that version number, your program is going to attempt an operation that will not work with that version number anymore. So the chances are low, and it should not happen if you have spelled out everything that you actually want to do and that you want to access down here. But there is a small chance. And for safety, we have added this v3 flag, this v3 modifier here in the middle, so that you can be sure that if you keep it, it is going to be backwards compatible. Now, another thing here is this best effort call. Now, this one is for people who want to deploy applications and you don't know what kernels they run on. If you write a regular Unix utility and it becomes part of distribution packages, and these get installed on different distributions, you might not control on what kernels this gets executed. Now, this is the feature that you use when you are in that scenario. What it will do is it will probe whether Landlock is available to your process, and it will opportunistically enable it to the best extent that it can. Now, for example, Landlock v3 lets you restrict the file truncation operation, whereas Landlock v1 and v2 don't let you restrict that. If you use Landlock, if you have a kernel that only has Landlock v2, you cannot drop that permission to do truncation, and the processes will always be able to do truncation, unfortunately. But at least you can drop the permissions to do all the other operations. And this is what best effort does. So if you put that in the middle, you know that your program is definitely going to work as long as the constraints that you give here are really the things that you need. Best effort also falls back on doing nothing sometimes. If the kernel that you run on is just too old, or if it doesn't have Landlock compiled in, or if it doesn't have Landlock enabled, we have tough luck and we have to give up on it. If you call it with best effort, this will not return an error. So here's an example. This is an image converter. It's a classic Unix utility, I would say. It reads an image from standard input and it writes the image to standard output as a PNG. Now, this is in Go, but I hope this is still readable for people who are not that familiar with Go. Now, we use landlock v3.besteffort.restrict paths. Note, we don't pass anything. Why don't we pass anything? Well, we don't have to open any files here. So we don't have to pass anything that we're going to use because we're not going to use anything. If you call it like this, any file open that we're going to attempt in the future is just not going to work, or any other access to a file. And then afterwards, we start processed untrusted input. And you see, this is the second phase here. If this was a C program, this would be even more risky. C programs have a tendency of doing a lot of stuff with pointers in the media parsing libraries, because this is just fast. And the problem with that is, of course, that doing things with pointers is fast, but it's dangerous as well. And sometimes people mess up, right? And especially in cases like these, you can see I'm not saying what the file format is. So we might pick one of many file formats that happen to be compiled into that library. Who knows what is getting executed there? So this is an example how you can make an image converter which does not have access rights to other files if the decoding is exploitable. This is another example. This is a Wiki software. I use Wiki at home, and I've written it myself in Go, and it has the following phases here. In the first phase, it sets up some object as a handle to our storage for the Wiki pages, and this library stores everything in this directory that we pass as a command line flag, and then we set up some HTTP things here, and we create an HTTP server, and then we call net.listen. Now this opens the network socket for listening, and then we drop the access rights, and only then we start accepting connections on the sockets that we listen on. Now this is also, by the way, an example of a program where I had to slightly rewrite the original program code to make it work. When you write web servers in Go, you will oftentimes in examples see that people call a function like, I believe, http.listen and serve or so, and that one does both of the listen and serve steps together. But in reality, listen is part of the initialization phase, and serve is part of the handling of the HTTP requests. If we split this apart, I'm using the lower level routines here. If we split this apart, then we can start to listen before we drop permissions, and that lets us to drop the permissions for the listen address. Now, what might not be obvious here, the listen address can be Unix domain socket. So if you use a reverse proxy, it can connect to the Wiki software over a Unix domain socket, which is a named file in your file system, and use that rather than a regular TCP port. So this is the Go-Landlock example tool. It's called Landlock Restrict, and what we do here is we create a little home directory. This is a technique that is for some ad hoc sandboxing of existing applications. It's quite useful if you want to just do it yourself without modifying it. And what we basically do is we create a temporary directory somewhere, and we just assign our home environment variable to point there, and then we call landlock restrict and invoke bash with it. And here is where the rule is specified, where the landlock policy is specified. So we are going to use user and lib and etc as read-only directories, and we're going to give read and write permission to the home directory and to dev. The dev directory is only used for a few devices. This could probably be more fine-grained, but for the example, that's enough. And then here in this red box, we are in that shell that got started by landlock restrict, and we can list entries, and we can see that we are in this directory, but we can't list the directory above. And I'm going to demo this to you in a different shell here. So here's our landlock restrict tool. We want to restrict with version 3 of landlock. The default is to use the best effort mode, otherwise we would have to pass the strict parameter. And we want to have lib, let me see, user lib etc. So user lib and etc are read only, and then home is read write and dev is read write as well. I have actually forgotten to create a home directory, so I'm going to make one. And And finally, we'll invoke bash with it. And there we are. We are in this directory, and we can see what's in the directory above. We can cd into other directories, but we can't really see what's inside. So there you go. We are in a sandboxed environment here. And if you create this as a script, maybe you use the normal utilities to create temporary directories and so on, you can relatively easily take applications and sandbox them. I have taken a computer game, for example, and only run this in a sandboxed environment. To that computer game is going to look like any other home directory. It probably doesn't access the password database to find out what your real home directory is. So in most cases, these applications just work that way. Yep. Yes, and now we have to talk about the limitations as well. Now this is going to be the more complicated chapter of this talk. And so there are a few things that Landlock processes can never do. So you can't manipulate your file system topology. So I can't mount in this directory here anyway because I'm not root. Right? But if I were root, I still wouldn't be able to do it because I'm in a landlocked environment. Now, so you can't mount, you can't pivot root. Those are all things that change your file system topology. This is of course necessary because otherwise you would be able to move parts of your file system under other parts where different restrictions apply, and therefore this is currently not permitted. Also not permitted is the executing sudo root binaries such as passwd and others, and that's called the no new privs flag. So you have to enable that, and the Go library does it for you already. You can look it up on the prctl man page what that means in detail. And then of course there is restricted use of ptrace. Ptrace is the system feature that lets you debug other processes. So that's how GDB works, for example. And of course, if you debug another process, then the debug process can be seen by the process that debugs it. And so that the debug process shouldn't have things in it that the other one isn't supposed to see. Therefore, ptracing only works inside, from the outside into a landlocked domain or into a landlocked policy, and it doesn't work the other way around. And then finally, Landlock is in development, so there's a few things that don't 100% work yet, but there are many things that do already work, and they're quite useful. So most of all, it's not able to restrict all of the operations yet that you can do in Unix. And this is a picture of what operations are permitted and which aren't. So, and I categorize this in three big groups. So in the middle, there are the configurable operations. Those are the ones that Landlock lets you talk about and which Landlock lets you make part of a Landlock policy. And then there is the set of forbidden operations. I already talked about some of these, like getting new privileges, manipulating the file system topology, ptracing, and also reparenting files between different directories was not permitted in version 1 of Landlock. And then third, there is the always permitted set of operations. This is probably an incomplete set. We might discover one or two more. But these operations are simply not supported by Landlock yet, which means that unfortunately they stay permitted for a process that uses Landlock. So you can still use stat, for example, and observe that a file exists. Or in version 1 of Landlock, you can still use truncate and truncate a file, even though you don't have write permissions to it. Now in version 2 of Landlock, we fixed the reparenting of files, and that means there is a new access right in Landlock which lets you say which files are supposed to be linkable or movable between different directories, or you say which from which directory to which other directory are you permitted to refer files. To link files back and forth. And then in version 3 of Landlock, we also added support for truncate, and that should hopefully conclude the list of operations for modifying the contents of a file. So when you use version 3 with best effort mode and you don't give the read permissions with the RWDirs, then also with file truncation it won't be possible to change the contents. And then there is, of course, a few things that are being discussed for the future, and at the moment the following patch sets are in flight. So chown, chmod, set exheader for modifying these file system attributes, who owns a file, what access rights does the file have, and other attributes. And ioctl was sent out, or in an early version at least. And then there is a longer going patch set already for networking support, and that's of course different to the existing restrictions that Landlock can impose, because this is not file based, but it's going to be network based. It's going to be more like a new category of rights that you can use in a Landlock policy. Well, and this concludes the big part of the presentation, and I want to round trip to the key point, and the key point is, of course, try it out. And this again is the little code snippet that you need to use in your Go application. If you want to use Rust, then I encourage you to have a look at the Rust library, which is also on GitHub. And if you want to use C, then I would encourage you to look at the example that ships with the kernel source code, and also at the weblog articles and other discussions that we have had. And of course, we have a mailing list where you can ask questions if you're interested in this. So this is the mailing list and how to subscribe to it. You can also write me an email. Here's my PGP key if needed. And thank you. And here's finally some more links, right? This is the source code for the Go-Landlock library. In this GitHub project, you'll also find the Rust version of it. There's documentation. There is documentation on Landlock itself, which is part of the kernel and part of the kernel docs. And finally, the slides for this talk are also available on my website, and there is a write-up of this talk on my website as well. And if you want to use C, or if you want to use a language other than Rust or Go, I would encourage you to also have a look at the other articles on my weblog where I go into more detail about how to build best effort fallback behavior in Landlock. There are a few twists, unfortunately, but they can at least nicely be encapsulated in a library. Okay. Thank you very much.